Hello, and welcome to the next exciting installment of Digital Design. The topic of this video is the art of managing complexity. So our fundamental question here is, how do we design things that are too big to fit in one person's head all at once? Engineers have a variety of techniques to address this problem. One is abstraction, another is discipline, and another are the three Y's: hierarchy, modularity, and regularity. Abstraction is hiding details when they aren't important. So, for instance, if we wanted to understand how a computer worked, we could start with the quantum mechanics. Ultimately, there are some electrons moving around in a lattice of atoms. Their positions and momentums are governed by quantum mechanics, and we could solve the wave equation for each electron, but trying to do that for vast numbers of components all at once is completely intractable. So instead, we'll move up a level of abstraction to devices. We'll define things called transistors that are made out of doped atoms, but that we can treat as several terminals with a relationship of voltage and current between those terminals. Moving up in abstraction, we'll get to analog circuits. So an analog circuit might be something like an op-amp or a filter that has an input and an output. It's ultimately made of devices, but we don't have to worry about the exact arrangement of transistors. We can just call it an amplifier. Continuing up, we'll move from the analog to the digital domain. We could define logic gates that take zeros and ones in and put zeros and ones out. Then we could talk about logic built from logic gates. So for instance, an adder or a memory could be comprised of many logic gates, but we can treat it as a box with a relationship between input and output. We can combine these adders and memories to make things like data paths and controllers, and that's a level we'll call microarchitecture. Going up from there, architecture is the programmer's view of a system. So the architecture of a computer would consist of the instructions that the computer can run and the registers inside the computer. Next up, we could talk about operating systems. So we might talk about a device driver. You could, for instance, open a device driver to access the keyboard and then read keys that were typed without having to pay attention to the exact pattern of zeros and ones moving across buses. And finally, up to the world of application software, where you could write programs that, for instance, print something on the screen or play a video game or do some kind of calculation. And ultimately, those programs rely on all the lower levels of abstraction, but when you're writing hello world to print something on the screen, most programmers aren't thinking about the wave equation of the electrons that are causing all this to happen. So that's the notion of abstraction. In this course, we will primarily focus on the middle levels of abstraction, from digital circuits up through architecture. We'll look a little bit at devices to understand what's underneath the hood, and we'll also get to some software. We're going to begin working our way up in Chapter 1, up from digital circuits and devices. Chapter 2 and 3 will develop logic, 4 and 5 as well. Then in the second half of the course, E85B, we'll begin with software and work our way back down, programming, then assembly language programming of architecture, and finally we'll meet in the middle with microarchitecture to understand how to build a digital system that runs the software. Discipline is another very important concept. This is the idea of intentionally restricting your design choices. So at first that seems counterintuitive. If you are limited to a smaller design space, why is it better? But a great example is the digital discipline, that will use discrete voltages instead of continuous. As a result, design becomes much simpler, and we can build much more sophisticated systems. For example, with analog television, we have continuous voltages coming in that might set the color of a pixel on the screen, and any noise in those voltages causes static. With a digital system, each pixel is represented by a pattern of bits, and we can introduce error correction, so even if there's some noise, the bits will still be recoverable and we'll get a crystal clear picture even in that presence of noise. So as a result, digital systems have replaced analog predecessors in so many different fields, and that's part of why this class is so exciting. Another technique for managing complexity is the 3 Ys: hierarchy, modularity, and regularity. So hierarchy is recursively decomposing a complex system into subsystems. Modularity is building systems with well-defined function and interface, which say the things that are modular have no side effects. Regularity is related to the notion of interchangeable parts. So as another example of the 3 Ys in engineering, let's take a look at the Model T Ford. The Model T Ford was introduced in 1908, and it was a famous early example of using interchangeable parts. So prior to this car, most cars that had been around for about 20 years were handcrafted by skilled tradesmen, and they were very expensive as a result. The Model T introduced mass production on a moving assembly line that greatly reduced cost. So Henry Ford laid out his manifesto to be able to build a car that an ordinary person could afford. Let's see how the 3 Ys apply. So we'll start with hierarchy. We can think of the car as a whole being broken down into components, such as the chassis, the wheels, the seats, and the engine. Then we can recursively look at each component. For example, the engine has cylinders, has spark plugs, has an exhaust system, and it has a carburetor. We can continue recursively, look at the carburetor. The carburetor has an air intake, it has an inlet needle, it has a feed pipe, and it has a coupling nut. So we have reduced from a very complicated object like a car that we can't understand all at once into simpler components such as a nut that we do understand. Next, let's look at modularity. So the nut has a well-defined function and interface. The functions of the nut include holding the fuel line to the intake elbow, preventing leaks, and being easily removable so that we could repair the system. The interface is standardized. It has a standard diameter, a standard thread pitch, a standard torque. So we can build a standard fuel line and a standard intake elbow held together by the standard coupling nut. And if something breaks, we can replace any one of them without having to custom craft the others. Regularity is the notion of interchangeable parts here. So we could buy this standard nut with its standard dimensions from any one of many suppliers, and that will drive down cost and increase availability. Another famous example of regularity on the Model T Ford was Henry Ford's statement, "Any customer can have a car painted any color that he wants, so long as it's black." By making all the cars black, all the parts became interchangeable, and they could be painted all at once, and if you needed another part, you could swap it out readily. So one of the key abstractions for this course is the digital abstraction. Most physical variables are continuous, such as the voltage on a wire, the frequency of an oscillation, or the position of a mass. But in the digital abstraction, we're going to consider a discrete subset of these values to define our zeros and ones. One of the early examples of the digital abstraction was a mechanical computer called the analytical engine. This was designed by Charles Babbage in the mid-1800s. It's widely considered to be the first digital computer, but it was built, instead of from electrical logic gates that do zeros and ones, it was built from mechanical gears, where each gear had 10 different positions, 0 through 9. And you could turn a crank and the gears would interlock and move each other, and they could cause the system to do things like addition and calculate tables. So Babbage got this idea. He was a mathematician in Britain, and he was very frustrated by the number of errors in tables of mathematical functions. And one day he and a friend were looking at these errors, and he said, "I wish we could just calculate this by steam." And after some thinking about it, he realized he could. He could build a machine that would calculate the tables. Unfortunately, every time Babbage got close to finishing a machine, he would come up with a better idea of how to do it even more elegantly. He'd abandon the work he'd been on and move on to the next system. Also, at the time, machining was nothing like it is today, and building thousands of interchangeable precision parts that all mated together was really pushing what the best craftsmen of the day could do. Finally, Babbage had a difficult personality, and many people had trouble working with him. So Babbage worked on this for most of his life before he had funding cut off by the Queen, and he died with the system unfinished after spending 17,000 pounds. That's 17,000 pounds of silver back in the day, enough to buy something like a dozen locomotives. And it left him with an unfinished machine that was ultimately melted down for scrap. So Babbage died a bitter and broken man, but in the 1990s, engineers revisited Babbage's plans, and with modern CNC machining, they were able to build the system from his plans and demonstrate that it actually worked. And in fact, 2 copies were built. There's a copy in the Computer Museum in Silicon Valley and a copy in the Science Museum in London. And if you go see, you can actually see the machine, and it calculates these tables. So returning to electrical systems, the system of 10 different gears is pretty touchy. It's much easier to only have to distinguish between 2 things, say 2 voltages. And nowadays we can build transistors that are extremely small, extremely fast, extremely cheap. They cost nanocents a piece. So that lets us build digital systems very easily. We'll call our 2 discrete values 0 and 1. A 0 might mean false, or a low voltage. A 1 could mean true, or a high voltage. And these could be represented with all sorts of different physical quantities, but voltage is what we'll typically use. We also have the term bit, which is short for a binary digit. That's either a 0 or a 1.